Okay, now we're good. So we'll talk a little bit about the basic results that you'll see. The correlation is the correlation between ROI A, ROI B, significant or not. So we're going to take a look at them. CONN is excellent at producing figures. A lot of options for just creating publication-ready figures, which is very nice. Most of what you will do, on the other hand, is choosing different options and thresholds. I mentioned things like a cluster failure with determining what cluster size is significant. CONN also has a built-in permutation function if you want to use that as well. So many different options for declaring what is significant or not. So we've already seen some of this. The second level result, you can display results of the seed. You can do a montage, see what the overlap looks like. What we're going to get to during the practical is using the results explorer. So similar to SPM, you'll see the results portrayed on a glass brain. In this case, my ROI was obviously the frontal right pole, and all these other clusters are what has passed these thresholds I've set up above. It gives you a table for any clusters that pass that significance level, and then you have other options for the results as far as displaying them, producing figures, and also displaying the effect sizes for different subjects. So you'll notice that, okay, 6 subjects, we're getting a lot of results here. Again, this is basically an F-test for this example that I've thrown up here. For what you'll want to do, if you may want to focus on a more restricted network of nodes, you'll see that with 6 subjects, it tends to erase the effect. If you're comparing groups, the effect is virtually going to disappear because, in this case, these aren't really different groups. It's very underpowered. Just be aware of that because of the parameters we're working within. For the ROI to ROI results, we can start to get into building these network graphs. So you'll see that for every ROI, we have a correlation for every other ROI in the brain, as opposed to seed to voxel analyses. So you can create figures like this, displaying what the strength of the connectivity is, what's the direction of the connectivity result, and also we can look at these so-called connectome rings. What do I have here? Yeah. These things you may also have seen before. These are so-called connectome rings. It's another way to look at it, but some people think it's more compact, more interpretable, and you can also organize them by networks or clusters to make it a little bit easier to look at. So just a couple caveats. Again, there are many different ways to look at the data, obviously. And as we talked about with the fMRI pitfalls lecture, what's most important is to set your thresholds and your options beforehand, before you actually look at the results. So that all being said, let's do a brief introduction to graph theory. Okay, so we know what we're looking at here. This is my neck of the woods. This is Michigan, and I'm going to focus on 4 cities in particular. There's Kalamazoo, which is a ridiculous name. I still can't get over that. I think it's hilarious. There's Battle Creek, there's Detroit, and there's Port Huron. Okay, this is from the Amtrak map. For my purpose, there's actually no Amtrak connecting Detroit to Port Huron, but I just added one in. So just be aware of that. You can't get there from here. But let's focus on 4 particular cities. Now, if I'm taking the Amtrak from Kalamazoo to Port Huron, I have to go through Battle Creek. There's no other way around it. I have to go through it. If I want to go from Port Huron to Detroit, I have a couple of options. I can go directly from Port Huron to Detroit, or from Port Huron to Battle Creek to Detroit. Take the scenic route. Obviously, going from Port Huron to Detroit is a lot cheaper, more efficient, easier to do, and that would make more sense in a lot of cases, right? Not many people go the other route, but it's possible, is the main thing. Now, if I assign a number to each of these cities, like Battle Creek is 0, Kalamazoo 3, Detroit is 1, Port Huron is 2, I can compress all this information into what's called an adjacency matrix. So keeping in mind that these represent cities, and the train tracks connecting the cities are connections in a literal sense of the word. If I represent this like this, let's call this train tracks edges, connections between different nodes, and let's call the cities nodes. A node that seems to have connections to a lot of other nodes we'll call a hub. And we use this term in everyday language, right? Atlanta Airport is a hub because it's gigantic and it connects to many, many other airports all over the world. Same thing here. If we collapse this into a matrix with, our indices on the x and y axes, we can fill in each of these cells with a 1 or a 0, a 1 indicating a direct connection between those nodes. So if I go across from here, I think this was Battle Creek to Port Huron, let's just say, that one is going to be filled in with a 1 because they do have a direct connection. This diagonal is going to be 0. We're not going to consider that a node connects to itself, just for practical purposes. And you'll also notice that this matrix is symmetric. So 0 over here, if I flip it over a mirror image, it's going to be the exact same. So some people just choose to focus on the upper triangle because the other information is redundant. Yeah. And something like Kalamazoo, it, say, can connect to Battle Creek, but it cannot directly connect to any of the other ones. Right? So simple example, makes sense. And if you're actually riding a train, riding an airplane, I mean, the exact same computations apply. How expensive is this to get from point A to point B? So the upshot is we can also call this collection of nodes and edges a network, right? They're connected, there's communication between them, there's different ways to get from one point to another. And it can be represented as a collection of nodes connected by edges. Later on, we'll make this more sophisticated. We can talk about the strength of a connection, which I'm kind of stretching the analogy here, but it might be like how fast the train can go from Kalamazoo to Battle Creek. How long does it take? How bumpy is the train? Things like that. Now, if I expand even farther, I go on a macro scale. Okay, so I was focusing on one state there, but if I look at the entire Amtrak map for all of America, you'll notice that there, it's a little weird at first, but there is some structure to it. So what things pop out to you looking at this Amtrak map here? There's no, yeah. That's the right answer, yes. There's no Amtrak in Columbus. Very sad. There's a Greyhound, though, which is just pretty gross. Yeah. Yeah, that's a good observation. I hadn't thought of that. But yeah, Chicago is definitely a hub in that it seems to connect a lot of these distinct regions. Yeah. There's also a lot of clustering going on, right? So things like in California or the Eastern Seaboard, there's really high traffic connections between all those different nodes. And they color code them on the Amtrak map, red is more than, say, 5 trains a day. So these really high traffic areas, obviously, between New York and Philadelphia, New York and New Haven, I've taken that one a lot. There's a lot of trains, a lot of frequency. But if you want to get from someplace from like Miami to, Vancouver's not in the US technically, Miami to Seattle, for example, it is possible, but it takes a really, really long time. You have different options for how to get there, but if you worked it out, you would do this, right? You go to Expedia or whatever, and you would try to find what's the cheapest and the quickest way. And you might have different weights for what you consider to be more important. If I have a lot of money, cost doesn't really matter. Time is really important. If I'm on a budget, time is not as important, and money is more important, right? So different ways that we can weight the importance of these edges. All right. So I'm using that as a segue to talk about some of the basic terms of graph theory. We talked about nodes and edges. Those are just like cities and train tracks. And we can also, when we go out into a bigger scale, talk about modularity, that clustering of different connections of nodes. And modularity has a technical definition. It's when is the density of intramodular connections greater than intermodular connections. So when I looked at the graph of Amtrak across the entire United States, there was really high density in the eastern seaboard. New York, Philadelphia, or Pennsylvania, Connecticut, for example. And that's much higher between that and, say, Chicago, even though there is, say, a connection there. So if we have something like two very distinct clusters of connections, okay, let's say the size of this node is the size of a city, and green is, and the color coding is something like, let's say that green is Europe and red is North America, right? And let's say we're looking at plane travel now, right? There's a lot of plane travel between all the cities in North America, but there are also some between the ones between Europe and North America as well. But it's not as frequent because it's very costly to do that kind of trip. It takes a lot of time. So applying this to something like these functional connections we're looking at, think of the functional connections between different parcellations of the brain as edges and the parcellations as nodes. Exact same concept. And here's some applications for it. This is by Geerligs et al., 2015. But let's say instead of color coding for continent, I'm color coding for different functional networks, let's say. And within that, I can see what the strength of connections are between different nodes in a particular network, and also between different networks. And here, this was a way to try to distinguish between aging brains and younger, healthy brains. You'll notice that there seems to be more functional segregation between the different networks in a younger brain. And as you get older, there is more of a mixture between the different networks. It's not as, say, modular, to use that word. There was a book written back in the 1980s, Modularity of Mind. Has anybody come across that? It wasn't written by a neuroscientist. It was a philosopher, actually, Jerry Fodor. He used to teach at Rutgers, I think. I think he passed away recently. But it kind of speaks to the same thing. How actually functionally segregated is the mind, and how does that map onto these brain structures that we see? This has become a pretty, well, I've seen it quite a bit, not just looking at functional connectivity, but also, say, something like machine learning classification between older and younger people. It seems to be much easier to classify in younger people, maybe in part because they have this really distinct kind of functional architecture that makes it easier to make distinctions between different classifications. Okay, so let's see here. This is kind of a recapitulation of what I was talking about. As far as nodes and edges, again, looking at air travel, there's different resolutions you can look at, right? So first we looked at a state, and then all of America with Amtrak. Now we can look at airports in the entire world. You'll notice if each of these are color-coded for where's their greater density, say within a particular geographical area, then between them we can color code them according to certain, say, thresholds that we set. And as we keep zooming in on a certain area, like let's say the Middle East, you would notice that what airports tend to mostly connect to other airports can be dependent on, say, geographical features, political features, not just, say, bodies of water and terrain, but also, borders of countries, things like that. So how do we determine exactly when a module is a module? How do we do this so-called community detection theorem? One of the most popular ones is something called the Louvain algorithm. You'll come across this a lot. As far as I know, I don't know if you're able to select a particular algorithm that the CONN toolbox does. I believe it's based on something like this. But for example, if you want to really go in depth, you could export all the data into a brain connectivity toolbox and use a different type of algorithm, depending on your level of experience with it. So it's a pretty simple concept. If I start out with, say, a bunch of nodes like this, and here's all the connections, what if I first start out saying that each of these nodes are individual networks, individual communities, right? And I say, well, is, say, if I make node 1 and node 2 part of the same community, like with one of its neighbors, does this cutoff for modularity, I haven't shown the equation, but there's an equation to determine whether the, say, correlation coefficient is above a certain threshold or not. Does that tend to make this a stronger modularity index or weaker? If it's stronger, assign it to the same community. If it's weaker, leave it alone. And then test the next one. Test this one with this neighbor. Does it increase the strength of the community, yes or no? If it does, assign it to the same network. And you might get something like this after the first iteration, right? You can do multiple iterations depending on what kind of resolution you want. So you might then say, well, I want to break this down further into, like, say, a single node that encompasses the entire visual cortex or parietal cortex and so on, and get something like this. I could break that down further and run another pass of this Louvain algorithm, and I could get something like right hemisphere, left hemisphere. And if you look at those connectomes, you would see how those things are parcellated on different scales. So let me show you kind of a different perspective on that. In a graph theory analysis, you have control over something called a resolution parameter. So I talked about zooming out from the state to the country to the world. Similar idea when we're talking about connections between different parcellations of the brain. Now, again, as far as I know, there's no resolution parameter setting in the CONN toolbox. I'm telling you this in case you want to kind of take this up a notch. But if we have a connectome like this, again, this is very finely parcellated, but you can see that that we have these larger color codings for grosser, larger anatomical areas, such as the frontal area, kind of temporal parietal, medial, say, motor areas, and so on and so forth. Those all tend to group into similar clusters, right? And likewise, I don't know if this is a good graph to show this, but if you use something like MR-Trix, for example, it's a diffusion analysis toolbox. You can also generate these connectomes, and you would see you could kind of slice this down this diagonal to get a really clear separation between left and right hemisphere. Again, depends what the resolution you're looking at is. And you can tweak this resolution. You can increase it on the right here. And this is almost like how many different connections am I going to allow into this node? If I set an upper boundary, it's almost like I can't allow any more connections in here. In that case, below a certain cutoff, assign this connection to another particular community. All right. And this is used typically to, create biologically meaningful modules. It all depends on the scale that you're looking at. And lastly, threshold. Just blew through that. And lastly, thresholding, in which if there's a correlation coefficient below a certain value, we don't consider that a valid edge. We simply ignore it. And it doesn't have any, bearing on whether we cluster these into communities or not. Okay, choosing nodes. So, I've told you about how you can, create these different graphs, but how do you actually select what nodes you're going to be working with? The default that comes with CONN toolbox is technically the Harvard Oxford. If you wanted to, though, there's an analysis with FreeSurfer based, again, mainly on anatomical landmarks called Desikan-Kiliani. So if you wanted to, you could take that, and if it's, say, formatted appropriately, import that into the CONN toolbox. We'll be trying that out in a second. You could do it based on meta-analysis, based on different functional search terms, for example. Dozenbach, I believe, has an atlas of this one. Or it could be multimodal, for example, Glasser. This is a 2016 paper, I believe. And that's regions that are based on a combination of cortical architecture, functional activity, connectivity, and tract topography. So a lot of different options available for you. Again, it's up to you. We'll be using that default atlas for right now, which is based on anatomical features. But yeah.
Sorry, before we get too far, the algorithm.
Yeah.
Can you go over again? So it's looking at node A to node B.
Yeah.
Sense that correlation.
Mm-hmm.
And then it's seeing whether that adds to what?
Yeah, there's a certain modularity index, and you'll set a threshold for whether, if I include this neighbor with this, say, seed region that I have right here, if this increases this modularity index, which is a formula, sorry, I don't have it here, but it's pretty easy to find. If it increases, keep it in. If it decreases or says it's 0, try the next neighbor. And you do that for each one successively until they start to stabilize around a certain collection. Mm-hmm. Okay. So as you'll see in a second, we will then create, we can create figures like this, in which case these voxels or ROIs serve as nodes and the correlations are like edges. So you get this type of spider web here. Again, you include everything. It tends to be, pretty all over the place because it's similar to just testing everything all at once. But you can restrict it to subsets if you want to. Last slide here, different graph measures that you can use. So this is mainly for, some of these are thresholds, so degree and cost, for example. If I have a node that only has, one connection to another node, do I include that as part of a network or no? If I'm only looking at hubs, for example, maybe I make the degree very high as a way to restrict that. Or cost is proportion. So let me think here. But once you have that type of threshold set, you can also use different methods to determine whether there is what the, let's say, strength of the network is. So a clustering coefficient means if there's one node and its neighbors are connected, let's say, then it has a relatively high clustering coefficient. Right? We're not going to cover every single one, but there's also local efficiency, for example, in which case, if I have a node and all of its neighbors are very strongly connected, it has good local efficiency. So that particular node, it could have relatively strong connections to all of its neighbors, but in that case, we're only looking for local efficiency, what the strength of all of its neighbors are.